Okay, exam review video part 10. Phase diagrams. We had tried to squeeze phase diagrams in the last video and just wasn't possible. So today we're going to look at a phase diagram. This is a phase diagram for water. Now, you need to remember that most phase diagrams are going to look like this. Most of them are going to have a solid, liquid, and a gas portion. There are some funky ones out there that have two different kinds of solids. Sulfur does that. But in general, they all have solid, liquid, and gas. CO2, we looked at CO2 in our notes, but today we're just going to look at water. So what's on here that's of importance? What's on here that's of importance to us? Well, the first thing that's important is that we notice that a phase diagram plots pressure versus, oh, you can't see, but I know what it is, temperature. Pressure versus temperature. Why not Kelvin? Because Celsius is more convenient, okay? In the gas laws problems, we have to use Kelvin, and these we don't. Now, obviously, you know where you can see where solid, liquid, and gas are. What you also need to know is all of the phase changes that take place at these boundaries. So solid to liquid, you need to know is melting, liquid to solid, freezing. Anytime you cross that line, that's the phase change you get. Liquid to gas, that's boiling. Gas to liquid, that's condensation. Solid to gas, that's sublimation. The reverse is called deposition. I didn't write all those on there because they're in your notes. You can go look them up. You need to know those phase changes, and you need to remember that along that boundary, along this boundary, anytime you're here, you're either subliming or deposing is the verb for deposition, or you're doing both. If you're on that line, if you're crossing the line, you're doing one thing or the other. If you lie along the line, the two are in equilibrium with each other. You need to remember what this place is. This is the triple point where all three phases coexist. They're all in equilibrium with each other. Isn't that neato? And the triple point helps us know what's going to happen. So how can we make water sublime? What would we need to do? Well, we need to lower the pressure. So if you had a chunk of ice and you lower the pressure significantly, you could make it cross like from here to here, and that would give you some sublimation. Now, why is a pressure of 1 atm marked? Is that because that's standard pressure? Yes, that is. That's standard pressure. And so let's go over, and right here it says MP, that's normal melting point. Normal melting point for water is 0 Celsius. This corresponds to 0 Celsius. That's the normal melting and freezing. Now it's melting if we're going this way. It's freezing if we're going this way. So that's the normal melting and normal freezing point at 1 atmosphere. If we keep going across, we get to this point, which says NBP for normal boiling point. Water normally boils at what temperature? 100 Celsius. Okay, so if you're given a phase diagram and you need to find the normal melting or normal boiling point, you have to go to 1 atm or the equivalent and look at what temperatures those happen. Normal freezing point, melting point, normal boiling point, or condensation point. Not that I've ever called it that, but you could call it condensation point if you want to. Okay, what else is important here? Well, it's important to note that you can predict how to change from one state to another. If you're at solid, how can you become a liquid? Well, you just need to figure out how to cross the boundary. That's an increase in temperature. That's an increase in pressure. Increasing pressure probably wouldn't get us to change solid to liquid, but increasing temperature would. Could you increase temperature and lower pressure? That's what that is. That's cool, huh? How can you get water to boil at a lower temperature? Well, if you've got liquid water in your here, let me put it a little bit closer. If you got liquid water in your here, how can you make it boil? Well, you can heat it up. You can increase the temperature, and we'll cross that line and boil. We do that all the time. Or you can lower the pressure. If you lower the pressure, you cross that boundary, and your water will boil. We did that in syringes in class. Okay, so my best advice on phase diagrams is go back to one of your old Edline worksheets and look over it to see if you can answer the questions. If you can, you're good on phase diagrams. If you can't, you're not good. Oh, by the way, up here is called critical point. That's why the person who made this put a C on it. That's the point where the boundary between liquid and gas go away and they blend into something called supercritical fluid. That's how coffee beans are decaffeinated. All right. Along the lines of boiling and all that stuff, I wanted to talk about vapor pressure and boiling today. I'm going to scroll back down to it and do it on the bottom. Remember that the vapor pressure is the pressure exerted by the surface of a liquid. Vapor pressure. Why am I still in that goofy blue color? Let's get some hardcore black here. Get it? I like heavy metal. Vapor pressure is pressure exerted above a liquid by the gas, by the vapor above a liquid. Okay, that's pretty cool. And boiling occurs. Boiling occurs. Oh, I hate spelling the word occur. Occurs when PVAP, that's vapor pressure, equals or exceeds PATM, atmospheric pressure. So when we push hard enough on the molecules, we heat them up and make them move faster and faster and faster. Remember, temperature and kinetic energy are directly related. In fact, temperature is a measure of kinetic energy. I'm going to write that in for you. Temperature is a measure of average kinetic energy. Okay, so when we heat it up, they have more and more energy. They're moving faster and faster. Remember, kinetic energy is energy due to motion. They're moving faster and faster and faster and faster. And if they have enough energy, they can escape. Cool? Cool. Now, so when we boil, whoops, I dropped the pen, silly me. When we boil, we give them enough energy that they can escape the liquid phase and become a gas. Cool? So what in the world is evaporation? Is it the same as boiling? No, evaporation is not the same. Evaporation is the random escape of liquid molecules into the gas phase, liquid to gas. And it's random. It happens at all temperatures. It's obviously going to happen more at higher temperatures, but that is not boiling. Evaporation only occurs at the surface of the liquid, nowhere else. Cool? Whereas boiling, the particles actually within the surface of the liquid can get enough energy to escape. Cool? All right. What else do we need to talk about vapor pressure and boiling? I think that's pretty much the gist of it. I'm going to pause while I think about what to do next. Okay, luckily I did pause it because I thought of one more thing I wanted to talk about. I want to talk about boiling in the mountains because I used a question about this and I had some people miss it. What's true in the mountains? In the mountains, the atmospheric pressure is lower. Why is atmospheric pressure lower? Because there's a smaller column of air above you, okay? There's less air pushing down on you. What does that mean about water? That means water boils at a lower temperature because there's less pushing down on it or holding the water molecules in the liquid state. So if you're in the mountains, you have to cook your food longer because the water boils at a lower temperature. That means the hottest it can get is 92 Celsius. And so you all know that if you have something set at a lower temperature, it takes longer to cook it. And so that's why we have special instructions on brownies and cake mixes and all that jazz. Cool? Cool. Okay. Speaking of brownies and cake mixes, let's talk about thermochemistry. You can see a list of topics I wrote myself so I wouldn't forget anything. And let's just dive right in. Alright, so first I'm going to start with a couple little definitions. Heat is the flow of energy. It's very important you understand heat is flow of energy due to difference in temperature. So if you put your hand down on the table feels cool because energy is flowing from your hand into the table. If you put your hand on the table and the table's hot, that means energy is flowing from the table to your hand. Temperature, we already spoke about. That's a measure of average kinetic energy. And then we'll talk about specific. Well, let's go ahead and do specific heat. Specific heat is the heat or energy. Remember, heat and energy are kind of interchangeable. Required to raise temperature. To raise 1 gram of a substance, 1 gram by 1 degree Celsius. And specific heat is important. You should remember that water has a very high specific heat. C is the letter we use for specific heat, and water is 4.18 joules per grams times degree Celsius. And that's given to you on your reference packet. That's liquid water, by the way. That's liquid water because frozen waters and gaseous water have different values. Now remember that liquid water has a high specific heat. That means it is difficult to heat up and takes a long time to cool off. And so that's how it can be possible for the pot that your boiling water is in, or the pot that you intend to boil water in, the pot can be really, 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 really hot, but the water is not hot yet. Or that's how a pool, remember that lady from the video? Pool. That's how a pool stays warm even when it's cold outside, or stays cold even when it's warm outside. Cool. We'll do heating curves and phase changes together. So let's move on to some specific heat problems, some example problems. Example 1. Ta-da! Example problem 1. How much heat? Now, remember that the equation for specific heat that we use, the equation that contains specific heat, is Q equals mc delta T, given to you in your reference packet. Remember that Q is heat, and that needs to be in joules. And let's see. Oh, we didn't say the amount of water is needed to increase the temperature of, let's insert in here, 50 milliliters of water. Whoopsie. Okay, so that's our volume. That's our volume of water. But what's true about water? Water has a density of 1 gram per milliliter. So that means 50 milliliters of water equals 50 grams of water. Is this true for any other substance other than water? Well, maybe there is another substance that has a density of 1, but not one that pops into my head. So this really only works for water, but it's something we do a lot. All right, so we're looking for heat, so we're looking for Q. Our mass is 50 grams. The specific heat of liquid water is 4.18. The change in temperature, final minus initial. Final minus initial. Final minus initial. And so that gives us 30 times 50 times 4.18, 6,270. Now, the first time students do these problems, they go, whoa, that was so big. But a joule is a very small unit, so it doesn't take a lot of I mean, a joule is relatively small, so it takes a lot of joules to heat up water, okay? So don't freak out about that. Here's an example problem 2. Ta-da! Don't you love it when I pause it and write out an example and it doesn't pause because you're watching it in real time? Huh, it's funny, huh? Okay, so example 2, it takes 10 kilojoules of heat, kilojoules of heat to increase the temperature of 50 grams of metal from 20 Celsius to 90 Celsius. Calculate C. Calculate this element's specific heat. Well, first off, I'm gonna go ahead and list what's given today. 10 kilojoules. You need to know that conversion. You can convert that. That is 10,000 joules. You must be in joules when you solve these problems. Mass is 50 grams. And change in temperature is 90 minus 20, or 70. Remember to do final minus initial, okay? So if it said from 90 to 20, it would be heat lost. There would be heat lost. Okay, now let's plug it in. Q equals mc delta T. We're looking for C. So we've got 10,000. We've got 50. We've got C. And we've got 70 here. So C comes out to be, I'm going to do 10,000. I like to do it this way. 10,000 divided by 50, then divided by 70, and that gives me 2.86. 2.86. What's the unit? Joules per grams times degrees Celsius. That's awfully high for a metal, because you remember what should be true of metals. Metals should have very, very, very low specific heat. So, whoopsie, I made that off the top of my head, and it didn't come out quite as low as I had hoped. All right? Okay, I'm going to finish quickly with heating curves. And remember that the opposite of this is true for a cooling curve. All right, this is a heating curve, and this axis is temperature. We're going to put it in degrees Celsius, and this is heat added or time, which can be in joules, kilojoules, or just time. It doesn't matter. So when we heat up a substance, this will be for water. This will be for water, but it could be for any substance. They pretty much always look the same. The temperature doesn't constantly go up. It goes up, then it plateaus, then it goes up, and then it plateaus, and then it goes up, okay? What's going on here? Well, remember that in this portion we have solid. This portion we have solid and liquid coexisting. This is liquid, liquid plus gas, and gas. And in this first portion, that's where melting is occurring. This is where vaporization is occurring. So, you know, I only have 30 seconds before I'm out of time on this video, so I need you to go and look this up. But remember, on the incline portions, we're changing, I'm going to write it right here, incline portions, we're changing kinetic energy. The plateaus, we're changing potential energy, or increasing potential energy. Remember, on the and I cheated in pause. Just remember on the incline portions, we're using Q equals MC delta T because temperature is changing, and here we're using HF or HV, which is heat of fusion or heat of vaporization.